Okay, so today I want to try to consolidate some of the stuff on effective field theory that we did. Some of the stuff I'm going to say is subtle, some of it is not, but needs to be said anyhow. So, okay, so I'm going to go through both those. If you want to, have any discussion about any of these things, there are some interesting things to talk about more if you feel up for it. Okay, so let's go through it. So what we did, we're doing this sigma model. We first did this tree level, where that was a good example of this just integrating out. So the phrase there is integrating out something. Then we schematically, or in some detail, went through it at one loop. That is the illustration of matching. The first thing I want to do today is another thing that goes into quotes, is power counting. So these are big buzzwords for effective field theory. So what's power counting? So at some level, it's the fact that we organize in the energy expansion. So we're counting powers of derivatives. So we have our matrix elements that start off as q squared over v squared plus it was q to the fourth over m squared v squared plus dot dot dot. So matrix elements got organized in the energy expansion. And then the Lagrangian did too. We started off as v squared over 4 trace d mu u dagger plus something like alpha 1. We called it trace, same stuff, squared. So 2 derivatives, 4 derivatives. But power counting is more than that. That's the oversimplified one. It's really what's relevant for a given order. So and what I want to first do is give you a wrong argument that shows you why it's an issue. Okay, so I'm being devil's advocate here. Okay, let's imagine that we have one of these Lagrangians. So we have L starts off as before, and way out at some place there's a term that's called alpha 100, because it's the 100th term in this series, and it involves something like trace d mu, d nu, d alpha, dot dot dot, u, d mu, d nu, d alpha, dot dot dot, u dagger. So there's a bunch of derivatives in it, 100 derivatives. Okay. In the Feynman rules, then we would have things that look like this if we take, P1, P2, K1, K2, something like that, a vertex like that. This ends up looking like alpha 100, that's over v to the fourth. That's not that important for my argument here. But then it ends up with things that go like K1 mu, excuse me, K1 nu, K1 alpha, K2 mu, K2 nu, K2 alpha, dot dot dot. Plus a lot of permutations. Okay, some of the times, so we're going to stick this in a loop in the next step. Some of the times these momentum will be P1s or P2s, sometimes it'll be K1, K2. So in the permutations you go over all those guys. But there are certainly ones that look like this, because you can have all those derivatives acting on one of the fields. Then in a loop, we would have integral. So I'm doing something that looks like this here. So here's my P1, P2. Here's another line. Here's K and K plus Q. Okay. I'd have integral d4k, k mu, k nu, etc., k plus q mu, etc. And there's two propagators, k squared and k plus q squared. Okay. Well, of course, that's badly divergent, right? So it's not the. But the leading piece is going to be pretty obvious here. It's when you take these k's go into each other. This will then end up looking like something like. So let's put a cutoff in there. So it'll be some lambda to the n, maybe 100, who knows. And then there'll be a term lambda to the n minus 2 q squared plus lambda to the n minus 4 q to the fourth, etc. So there'll be some energy expansion of this guy, right? With some coefficients in front of it. Well, this looks like a problem now for us, because if we try to write out the effective Lagrangian that comes out of this, the effective Lagrangian would be, well, there'd be some lambda to the, so it would be alpha 100, lambda to the n, and then the terms that go like q squared would go into an effective Lagrangian with two derivatives, so it'd be v squared over 4 plus alpha to the 100, lambda to the n minus 2, whatever that was. Trace d mu u dagger. And then there'd be alpha 1 plus alpha 100, lambda to the n minus 4, times the next guy, plus etc. So the result of this seems to be that to do the theory, calculate the theory, do we need to know alpha 100? To predict something. Okay. You may remember I started out differently. I just started out using the lowest order Lagrangian, and I used that in a loop. But should I have used one further down the line? Okay. This would, of course, be a disaster if it happened, because then your hopes of knowing the 100th order one is pretty weak. But it seems like I've just given you a proof that it contributes to order q squared. Okay? The answer is no. And the reason is what we call power count. Okay, I'll give you the answer first, and then we'll go through the way it's proven. Okay, so the answer is Weinberg's theorem. And let's give you the content of so we're imagining our Lagrangian there's a term with 2 derivatives, there's a term with 4 derivatives, there's a term with 6 derivatives, and the general term will just be n derivatives. So there'll be some coefficients of those n derivative terms. And in principle, you can use any of those in a diagram. So you calculate some diagram, here's some number of external legs. There's 4 external legs, and we put some loops in there. Loops. I don't know. There's a bunch of loops. Let's see. Is that the kitty cat diagram? There's the head. Okay. Anyway, so 1, 2, 3, 4, 5, 6 loops. 6-loop diagram. So we'll categorize this by the number of external legs and the number of loops. And at each of those vertices there, we could use the Lagrangian with powers of n. So taking one of those Lagrangians could be any one of those vertices, and this is the number of vertices using Ln. Okay, so if I could maybe have all of them be L2 except for one of them be L100. That could be L100, one of them there. Okay. On general grounds, by dimensionality, the matrix element is going to go like some energy or mass factor to the 4 minus NE. And that's nothing to do with effective field. That's just counting the dimensionality of a vertex. Okay. So and we see that here. If we have NE equals 4, like we have when we have this guy, that's in lambda 5 to the 4th, that's a dimensionless coupling constant, so it's dimensionless. In our calculation here, it's q squared over v squared. V has dimensions of mass, q has dimensions of mass, so that's dimensionless. So that's just by itself. Okay, but Weinberg's theorem says that this should go like mass or energy to the... Weinberg's theorem says it goes like e to the d in practice, where this E is the external energies. So, for example, V doesn't count in here, so this is just Q squared. Okay, and D is 2 plus the sum over all the different types of Lagrangians, the number of each type that's used times n minus 2 plus 2 times the number of loops. Okay, so let's explore what that means. If we used, so I'll do the example, pi goes to pi that we're doing the explicit calculation for. The matrix element we saw was, it started off as q squared over v squared. This guy came out of the true derivative Lagrangian, so n 2 equals 1, and the number of loops for that guy was 0. So number of loops was 0. The number with 2 derivatives was 1, but that 2 minus 2 is 0, so it just becomes out of energy squared. Okay, so that works. The next piece we had was something like alpha renormalized q to the 4th over v to the 4th. So there's q to the 4th there. This came out of n 4 equals to 1 and loops equals to 0. So we used, if you just took tree level and didn't do any loops, the 4 derivative Lagrangian worked with no loops. So 1 4 derivative Lagrangian with 2 there, no loops worked. Or we used the 2 derivative Lagrangian twice in the vertex. We used one up there, we used one down there. So it's used twice. And the number of loops is 1. So again, it doesn't matter how many of these you use, and 2 derivative Lagrangians don't cost you anything. But the number of loops does, so you're up to 4. Okay. But this then tells us that this is going to be true in general. That if we want order energy squared, we can only get that from the tree level. N2 is equal to is equal to 1. But basically n loops has to be equal to 0. Actually, if you use any number of 2 derivative Lagrangians, it doesn't matter. But you have to have n loops equal to 0. If you do e to the 4th, you can use n loop equals to 1, and 2 is equal to anything. Or n 2 is equal to or n4 is equal to 1, and loop equals to 0. E to the 6th, then you can do 2 loops. You can do 1 loop and 1 and 4, 1 from the Lagrangian and 4, or you can do no loops and use N6. Use L6. Okay, but our previous example wouldn't work then. It says that L100 with 100 derivatives contributes to only to e to the, if I use even one of those, 98 plus 2. So it starts at e to the 100 and higher. So I started off here with 100 derivatives. I pretended that I got down lower orders, but Weinberg's theorem says that that can't happen. So what's going on? So let's first prove Weinberg's theorem, and then you'll see what's going on. Okay, so let's come down here. I'm not going to prove it in general. but I'll just prove it by example, and you see how it works. The the explicit counting takes a little painful, but let's just do a loop diagram. Let's do it by an example. So we're going to do this pi pi goes to pi pi, and the L2 Lagrangian starts off like some energy squared, q squared over v squared, and let's just use that in loops. Okay, so starting off with that in loops. So if I do this, I do something that looks like this. This is some 1 over v squared happens there, 1 over v squared happens there. The matrix element is overall dimensionless, but this then has a factor 1 over v to the fourth from this. Some loop integral, that's a function of the momentum. Okay. Now you use dimensional regularization on this. Dimensional regularization doesn't really introduce any particular scale. So this ends up going like 1 over v to the fourth, but it has to be dimensionless, so you end up with some various p's to the fourth in dimensional regularization, up to factors of 1 over d minus 4 plus finite terms. But it's really just the dimensionality of the overall answer, and everything else goes like the momentum. If I do two loops, I do this and this. There's 3 vertices, 1 over v to the fourth, 1 over v squared, sorry, there, there, and there. So this goes like 1 over v to the sixth. Some different loop function, but just, again, just because there's no dimensional factors there, and it goes like 1 over v to the sixth, pi to the sixth. If I tried L4, L4 looks like alpha trace d mu u dagger squared. So there's alpha 1 there. Alpha 1 is dimensionless. Okay, because I've got 4 derivatives in the Lagrangian g to the fourth. So this goes like alpha 1 over v to the fourth, p1 dot p2, p3 dot p4 as a matrix element. So if I take that matrix element, the Feynman rule goes like that. So if I do a one-loop diagram with that, I get this guy. It goes like 1 over v, alpha 1 over v to the fourth. This guy goes like 1 over v squared. So I've just used one of these guys. So just by counting powers of v, it's 1 over v to the sixth times some loop integral. V to the sixth, p to the sixth, which is what Weinberg's theorem says it should be. If I use that in one loop, I get p to the sixth by Weinberg's theorem. So the flaw in my previous argument when I was being devil's advocate was using a cutoff. The cutoff fouls up the power counting. If you use dimensional regularization, there are no dimensional scales there, and you get this expansion with where you only need low order ones to make a prediction at a given order. Okay? So, we're almost ready to give out the overall rules. But can you ever understand the nature of that? It's really just counting dimensional factors there and then using dimensionless regularization. Okay. Next comment. This one is more trivial. This is measuring versus matching. So we went through the linear sigma model, but we can have theories that you can't do matching on. So you can't match if the theory is uncalculable, which is like low energy QCD to the at very low energies we have a hard time doing a calculation, so we can't match low energy QCD to an effective Lagrangian, or it could be unknown. Gravity is the case here. We want an effective Lagrangian for gravity. We don't know what the high energy theory is, so we don't know how to do this matching. So, but if you can't match, you still use effective Lagrangians, and you can still do loops, and you still renormalize. But instead of matching to the full theory, you measure the parameters instead. Okay, so that's the obvious thing that you would do. So there's not too much to say about it, but you will go through whole little subfields using effective field theory where you never talk about matching because there's nothing to match to. Okay, so here's the rules of effective field theory. Okay, systematically, how do you proceed? So you use only the low energy degrees of freedom. Which the example was the pions, not the heavy particles. You write the most general. The L effective consistent with the symmetries that you have. You order it in the energy expansion. You renormalize the parameters in this. Okay. This is done order by order. And here's where power counting comes in. You know what orders you have to do, how many loops you have to do by that power counting theorem. Most often it's one loop. Okay. Because we almost never work beyond one loop. The fifth step is you match or you measure. And then the sixth step is there are residual predictions. Okay. In the example that we did, the predictions actually are were in that loop function, BSTU, which had various things like log s over mu squared plus dot dot dot. Those are the residual predictions. You know, to some extent, the energy expansion, it contains some of them, but these guys are real predictions of the theory. They're not measured. Okay. Any questions? All right. I'm going to move away from the linear sigma model in a minute. Well, not completely, but let's just. I just wanted to say some things about the sigma model and real physics. Okay, we've been using it as a hands-on example of effective field theory. And we can do many things with it here. You know, so that's good. However, it's also equivalent to the Higgs sector of the standard model. Okay. If we write sigma as this v plus s e to the I tau dot pi over v. In the standard model, this v is 246 GeV. That's the Higgs vacuum expectation value. S is the Higgs. Pi's are the longitudinal components of the W. That can be made a lot more precise. The pi's really are the longitudinal components of the W. If you want to know how longitudinal W scatter, you can just look at how the pions of the sigma model scatter. It's exactly the same. So the matching calculation we're going to do here is also exactly the same as doing gauge boson scattering. Okay? And there's also the mass generation effect. Remember, we had G psi bar left sigma psi, which goes to G psi bar left V plus F psi, which gives GV gives the mass. So that's also exactly the same. Okay. The linear sigma model also is a good example for QCD at low energies. So the symmetry is the same. So L effective has the same form. We'll come back. I'm going to do some more of this when we do QCD. But the key feature here is the matching is different. So the alpha 1 and alpha 2 are different. And in fact, they're substantially different. If you just look at the numbers for them for the sigma model, and you try to put in some estimates of what the mass of the sigma should be, the S should be, the pattern isn't even the same. But the other modification is that the symmetry in the case of QCD is not exact. So, whereas the linear sigma model, I started off with an exact symmetry. I'd like to just briefly take a moment here to do that. To show how you can do you can get out the form that you're going to expect in QCD from the linear sigma model. Again, because we can do it directly. So if you wanted to break the symmetry, we can add, in the sigma model, we can add a term that looks like a sigma. Okay, so this is no longer invariant under rotation between sigma and pi because it's just one of the fields. Okay. So the potential then, v of sigma and pi, gets shifted. It has this minus mu squared over 2 sigma squared plus pi squared plus lambda over 4 sigma squared plus pi squared, and then minus a sigma. Okay, so choosing a positive actually is the right way to go, because then if you look at this potential, this is a tough one to draw well, but it has this feature that's exaggerated a little bit, that this minimum down there is lower, so the minimum on this side is lower than that side because there's a linear piece when sigma is positive. So this is sigma in this direction, sigma in that direction here, and the pi direction, if you want, is back that way. And this is v of sigma and pi. And then if I try to draw a circle here, that's about as good as my drawings ever get. That looks okay, right? So this circle is no longer flat. This point is higher than that point. Okay? And then, so just think, if you think about it, you see that, remember, the curvature here is the mass of the sigma. If I shift the field sigma by a constant amount, the energy goes up by the mass of the sigma. This previously, if I shifted the pion field around this circle, there was all the same energy, so the mass of the pion was 0. But now if you picture this here, as I leave this point, I have to climb up. So I've got a tilted circle, so there's a slight curvature there. So the pion mass is not going to be 0 anymore. Okay? So the one way to calculate this is you expand about the minimum. Okay, the minimum shifts a little bit, and etc. And I have, I have 6, 7 lines of algebra to do it. But you end up with the m pi squared is a over the vacuum expectation value, the first order. Okay, it actually, if A was a big number, there's nonlinear corrections to that also. Okay, but it's actually easier to get this answer by doing the effective Lagrangian, and the effective Lagrangian is going to look the same as if we did in QCD. So let's just do that. So let's get it by the effective Lagrangian. Okay, so recall that sigma plus I tau dot pi was what we called capital sigma, which we called V plus S U. So if I write the Lagrangian being A sigma, that's A over 2 times the trace of big sigma, which is A over 2 V plus S trace of U. I could, if I want, make this A over 4 V plus S trace U plus U dagger, since the same, I could have written this sigma plus sigma dagger over 2 if I wanted to. Okay, this is going to be the exact same form that comes out in QCD, except for that S gets removed. Okay, so then you integrate out S. And you know the answer is going to have the form L effective is an A V over 4 trace U plus U dagger, plus then there'll be some coefficient beta 1 trace U plus U dagger squared, beta 2 trace U plus U dagger trace d mu U dagger, etc. Okay, so you can get these terms. These terms all here break the symmetry, and then you just read off the pi and mass. Okay, the first correction is the only piece that I'm interested in is first order, so that sits right there. And I just, trace U plus U dagger is trace, 1, U plus U dagger has no linear term. If there was one, it would be traceless anyhow. The next term is minus tau dot pi. Actually, it's trace 2 plus tau dot pi over V squared. That's squared. So there's a 4 minus pi I over V squared times 2 from the trace. And so L effective then has A over 2V pi I. So you read off M pi squared is A over V. The same as before. Okay? It's actually much easier to do it this way. If you, the calculation the other way, it wasn't worth doing. But okay. So So that's basically my the end of the main development. We now know how to apply effective field theory. I could list various uses like QCD or gravity or the standard model or physics beyond the standard model. I don't think you get too much out of making that listing, so I won't. The one thing I do want to do before moving on, though, is I want to talk about Ken Wilson. And effective field theory. Wilson was actually very influential, and there's three things that come together here. There's his introduction of effective field theory, his treatment of the renormalization group, and his development of what's called the operator product expansion. the logic of these are all tied together, and this is the part that's somewhat subtle and gets abused in the literature an awful lot. So let's see if we can try to get straightened on it. Basically, in Wilson's use, he's not only integrating out heavy fields, heavy particles, but also the heavy, the high energy parts of light particles. Okay, so you not only are getting rid of the heavy stuff, but you're also taking, for example, gluons or pions, and you remove the stuff beyond some scale. We'll call this scale lambda here. Lambda is not the same as a renormalization scale. In this case, it's a separation scale where we separate the degrees of freedom into the light components and their high energy components at that scale. Okay. Technically, here's what you're doing. You take this path integral. Let's pretend it's the pions. The pi e to the I action. So the true action, whatever it is. This could be the linear sigma model, and we could have an S, and then we also integrate out the scalar. But here, what Wilson would have us do is he separates out the path integral into the stuff below this transition scale and the stuff above the transition scale. Okay, so less than lambda and greater than lambda. E to the IS, true. Okay. And this guy gets the calculated, integrated out. So this turns into e to the I S effective, which is a function of pi and lambda. Okay. So that we then end up having our effective theory is we take pi's only below some scale, and we have e to the I S effective. It depends on that scale. Okay, so that's Wilson's basic thought process. And his original motivation was really condensed matter physics. It's the Ising model was the original one. Where you've got the spin system, but if you look on a long enough distance scales, especially near the phase transitions, then what goes on very small scales doesn't make much difference, so you integrate that out and you write an effective Lagrangian for the big scale stuff. That's it. So here, let's make some comments. So this also then leads to the renormalization group. Okay. Basically, the parameters in L effective depend on lambda. Okay, and you can it's easy to see this. Let's take QED. In QED, we know the charge depends on scale, or But if I had a bare charge that depended on some scale, let's call it lambda 1, and I did the vacuum polarization, it's E squared over, I forgot to copy the exact number, I think it's 15 pi squared, log lambda 1 squared over mu squared is E physical, which is 1 over 137. But then if I change the scale, this thing, you'd have to have E 0 squared of lambda 2. If I change the scale, 1 plus dot 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 this thing with lambda 2 equals E physical, so that you'd end up generating a renormalization group equation for E squared of lambda squared to keep E physical fixed. Okay, so this is how Wilson sets up his renormalization group. Okay. It's also permeated, this thinking is permeated effective field theory. It's good in effective field theory. It's a good way to think when your degrees of freedom change. So an example is QCD, where the pions are the right degrees of freedom below 1 GeV, where like quarks and gluons so it's tempting to think of the effective theory as defined below 1 GeV. So the effective theory is defined that way, okay? Because the portion of the theory that you might consider the integral is if I had d pi greater than 1 GeV, that's pretty meaningless. Okay? So this is the way almost everybody thinks about pions and QCD. However, the subtle point is that it's not actually done in practice. Okay. And that's what causes the troubles most of the time. Okay, so most of the time you actually don't use it. And the logic here is that cutoffs are tough. Okay. And my example that I gave you before is that it looks bad, it's tough in power counting. Okay. If I had used the cutoff like Wilson says I should use, it upsets power counting. I put that in quotes because in fact it doesn't. Since you know power counting has to work, it always works out. You can, since the cutoff doesn't change the physics, you can always make it work, but it's always a little bit subtle to do it. So people then use dimensional regularization. So there's no cutoff. But then you are including I'll call fake or false info in loops beyond so if you're doing chiral perturbation theory where there is actually really a transition at 1 GeV, pions don't really exist above a GeV. The loop effects from the pions then is wrong. It's just there's nothing right about it. So you're making a mistake in doing so. But that mistake is high energy. So therefore it's local. So therefore all it can do is it just makes a change in the coefficients, so the alpha I coefficients. So since it's local, it can only change those guys. So in the end, there's nothing, as long as you match or measure correctly, there is no problem in doing that. The only difficulties come when you think using a cutoff and then calculate not using a cutoff. You often get into some mistakes. Okay. And then the fourth thing I'd like to talk about, don't think I want to do today, is this idea of the operator product expansion. Okay. The same thought process goes into this. So remember the idea of the operator product expansion is taking two operators at different points, and as the points get very close together, this gets expressed in terms of local operators, and in principle coefficient functions that carry any residual x dependence. Okay. However, what I didn't write out before is this Wilson's idea in proposing it has scale dependence here also. So this transition scale also plays a role there. And I want to explain that and then maybe come back next time and do it. Okay, so the logic is on why is there a transition dependence there? Well, there are some stuff. The high energy part is effectively local. High energy part means energy is greater than lambda. Okay, but there's also, in principle, renormalization that comes from low energy parts. Okay, so the example we'll do is something. I'll tell you what it is, but it will have a gluon going around it, and if the gluon had very high momentum, then that would be local. But if the gluon had very light momentum, it can propagate out and come back and hit these lines. So in this case, the gluon has both pieces that are local and non-local. And so if you want to separate out this, in the OPE, matrix elements of O that carry this index lambda associated with it will when you take matrix elements, in matrix elements. So when you apply it, you still have to include the low energy gluons up to some scale lambda. The gluons, or with E greater than lambda, get integrated out. And they're local. Okay, so the basic physics that he's capturing here is that some of the matrix elements, some portions of it, are local and others aren't, and we separate it out by this cutoff scale. All the local stuff goes into this coefficient here times a local operator. Then when you take matrix elements later on, you include the effects of the local operator. Okay. This is also this is done in practice. And this again is another one of these places where you get into trouble if you think in one way and use dimensional regularization in the other. So, a particular example that happens in the literature is if you're doing something in QCD, you calculate using a lattice. The lattice spacing provides a cutoff from the high energy degrees of freedom, but then you calculate using dimensional regularization. You have to work hard to match those two, and it's not always done. All right, I think I will stop there. I'll come back and I have two things I want to do to finish off effective field theory. One is I want to describe a little more detail what this operator product expansion is in practice by doing an example. And the other is even though it's not an effective field theory, I want to do background field renormalization at this point. And background field renormalization, and my logic for doing here is, one is it fits very nicely in with this topic. It's not uniquely effective field theory, but it fits. But I'm also thinking that it's possible that in doing this matching that we're going to do with the linear sigma model, that it might be good or best to do it using background field methods. And so I want to have that in the toolkit at the time we get to it. Okay, so that's where we go next. Anything? Yes?
So the Weinberg power cutting theorem.
Yes.
Does that only work for this specific EFT?
Well, it's designed for this. It works.
I mean,
The exact same power counting theorem also works in general relativity. The same formula works in general relativity. If you introduce heavy mass scales in the theory, let's say you're doing baryons, okay, then you can screw up your power counting theorem, okay? And so, but then people will go out and rederive different power counting theorems, and those theorems depend a little bit on your formulation of the effective field theory. So if you remember, well, the talk last Friday had talked about power counting, and in the relativistic version he gave up power counting. He got terms that had higher and higher contributions out of one loop. But some of those frameworks that he did for renormalization had power counting, and so it was a little bit of a contrast of the different power counting schemes. But in general, when you hit a new topic, you derive the equivalent of the Weinberg power counting for that, because it's really what tells you what diagrams you need to calculate. So the one I did is true for general relativity. It's true for chiral perturbation theory. It gets modified slightly when there are other masses. I think it's probably true always when there's only massless particles around, or particles whose mass is comparable to the energy that you're counting.
Well, wouldn't I know know in nuclear you also you have
Right.
bound states,
Right.
and they also affect the power count.
Yeah. Right. Yeah, bound states have the issue of being non-perturbative in the interaction strength, so that does screw up power counting also. But those are non-relativistic theories with a heavy mass scale around, so that's, you have to, as I said, you have to redo the expansion then in each for that. Okay, and you know, as we saw, using a cutoff tends to screw up the official theorems. However, what is often not appreciated in the literature is if you do use a cutoff, you can get exactly the same results using the same diagram. So you do your power counting using dimensional regularization, and then you just take whatever diagrams you've got there and do it with a cutoff, and you'll end up reproducing, in the limit that the cutoff is large, you'll reproduce exactly the same results as dimensional regularization. So it's actually doable. It's just,
But doesn't that also affect your power counting though? I mean, if you use cutoff with dimensional regularization,
yeah. So what happens is, much like that the example that I gave where I did use the cutoff, you have to renormalize your parameters order by order in the loop expansion. So if I wanted to use a cutoff scheme, in dimensional regularization, v squared didn't get renormalized. Okay? In a cutoff scheme, it will get renormalized. And anytime you do one loop or two loops, it gets renormalized. Two loops, it gets renormalized different from one. So basically, you have to go back and redefine your parameter v squared, renormalized parameter at one loop. You have to define your alpha 1 at one loop. But once you do those and you fix them to the same input, either matching or measuring, then in the limit that the cutoff is large, you actually get exactly the same predictions. Okay, and it's an interesting example to go through and do it. You know, Barry and I have done this in heavy baryon chiral perturbation theory, where you can see that the dimensional regularization comes from taking the cutoff to infinity. Okay? But then it actually raises this issue of, you can actually see when you do this then that by taking the cutoff to infinity, you get dimensional regularization. If you take the cutoff to some finite value like 1 GeV, you then can calculate what's the contribution to some process from 1 GeV to infinity. That's calculable now all of a sudden. And so you can separate out then the true low energy input from the high energy input. And so one of the cases that we've done there is ones where you find large corrections when you calculate it dimensionally. And then you can ask whether those large corrections come from the low energy piece where the effective field theory is valid, or from the high energy piece. And in the particular case we looked at, they come from high energy. And so the size of those corrections then is not a good prediction of the effective field theory. Only the low energy parts of that would be. So sometimes using a cutoff is good for answering questions like that. Where do various contributions come from? In principle, the end answers shouldn't depend on where you choose a cutoff, but at any given order, there is some dependence left over. Okay. Anything else? So that's one of the more subtle things about what I was talking about, that is often misrepresented in the literature. Anything else?